Welcome to today's podcast. In today's session, we have with us an expert from a field related to batteries. Ramesh Natarajan, a veteran with over 42 years of hands-on battery industry experience, will be asking our esteemed guest a host of technical questions. Hope you find this podcast useful to your business. Enjoy the session.
Welcome to this episode of my podcast where I have with me Mr. Alagheband. He is the technical manager at SST company since March 2018 and he is also the engineering and R&D department director at the biggest lead-acid battery manufacturer in the east of Iran for 11 years. He has a lot of experience in the research development department with a demonstrated history of working in the automotive industry with a Bachelor of Science focused in chemical engineering and a Master of Science in industrial engineering. He has done several presentations at Labat 2017, 18th Year ABC 2019, 17th ELBC 2020, 19th ABC 2021, Labat 2021 and 20th ABC 2023. He recently had a presentation at the Power On exhibition in Delhi, India a couple of days ago. That was on 9th January 2025. Now, Mr. Ali, do you want to say something more about yourself or your company before we proceed with the question and answer session?
Thank you, Mr. Ramesh. I'm really happy to have this meeting with you. And I hope you can find it helpful, and I can help the scientists in this industry to improve their the performance of their product by this investigation. As you already informed, my name is Ali, and I'm from SST Co, Iran. My company is a trading and technical company since 2017, and the main fields of the company's activity is defined in 4 fields. First, trading, second, production, third, research and development, and finally, technical service. At the end of last year, in 2024, we already start cooperation with the company, Indian company, Listing Consultants, that they are leading provider of technical consultancy and digital transfer solution for lead-acid battery industry.
Yeah, I think this time for the Power On also, you have been invited by Listing Consultants,
yes,
headed by Mr. Yudi,
yes,
as he's popularly known.
Yes, after we start our cooperation, Mr. Yudi informed us that there is a great conference and exhibition in India, 19th Power On, and then asked me to send my presentation, and I found this opportunity to be part of this technical.
As a convener of the conference, when I did get the feedback, people were very happy with this presentation because you...
Thank you.
Yeah, it was really good, and what happened was they got something new to learn about strontium in lead calcium alloys.
Yes.
And this is something probably which has never been discussed, at least in India earlier, and they were very happy with your presentation.
I already happy.
Yeah. Thank you. Now, how did the idea of using strontium in the positive grid alloy of lead acid batteries come about? Like, why did you think of doing this?
Yes. As a history of positive grid alloys, lead-acid battery manufacturers first start with antimony alloys, but due to high water consumption of lead antimony alloys, first PB calcium tin alloy were developed for MF and LMF batteries. By high polarization of the plate on discharge and eventually to capacity loss that we call PCL1 effect was coming from high calcium content. So, on the other hand, new application of lead acid batteries called EFB batteries need thin full frame grid with improved corrosion resistance. So lower calcium content can cause higher thin calcium ratio and improve the corrosion resistance. But decreasing the calcium content will drop the grid hardness and decrease the productivity of the plate making process. On that time, at the beginning, I researched about another element to be replaced by calcium. I found a presentation in ELVC from Furukawa Battery in Japan, and they introduced barium as a certain force element in this alloy. And I tried to use barium, but barium by itself is very hard to use. So, and it was not available in Iran. There was some.
It was hard to use. I'm sorry for interrupting. Hard to use in
because
casting or in the alloying.
In the alloying.
In the alloying. It becomes difficult to alloy.
Yes, because normally barium is existing as a ferroalloy. It is containing iron. And thus the melting point is very high, and also the impurity from iron is not good at all for the lead acid battery. Then when I search again, I found the strontium. Strontium has a master alloy. It is combination of aluminum and strontium with different percentage. Same as calcium aluminum master alloy. And very easy to use and very easy to found and very easy for alloy making. So that was the idea that I started thinking and working on PB calcium tin strontium alloy at the beginning.
Okay, was this only for corrosion resistance mainly?
Mainly corrosion resistance, but during our investigation we found many other advantages that I will explain.
Okay, but now in that case, once they put tin in the alloy and probably sorted out the corrosion resistance with the tin in the alloy, why did you still need strontium?
Mainly because of hardness. Because for pasting process, to have a strong structure to keep the paste, we need a strong and hard grid.
Okay.
So we need calcium, antimony, strontium to improve the hardness of grid. That's why that we need these types of alloy.
Not antimony. Antimony cannot be mixed with calcium, right?
Yes, sure.
So not antimony.
No, calcium and strontium.
Calcium and strontium to replace the antimony, the hardness of the antimony.
Yes.
Put the strontium. Okay. How did you choose the test samples for this strontium content? How did you arrive at the content? How did you choose the test samples?
Yes. Normally, for gravity casting, different percentage of calcium is using. From 0.05, 0.06 to 0.09 for grid casting. I'm talking about the grid casting, not punching and
not
expand metal.
Yeah.
I will explain the next steps that we are going to do for wide strip casting and narrow strip casting at the end of our conversation. But as a conventional alloy, normally I considered 0.09% calcium content. It is very normal in Iran with 1.2% tin. And then I tried to replace some amount of the calcium with the strontium. So I prepared 0.04% calcium content. Decrease the calcium content to less than half, and then replacing the remaining amount with strontium step by step. So we prepared 5 samples from 0.01 to 0.06 for strontium content alloy, and one as a reference alloy with 0.09% calcium without strontium.
Okay.
This was the concept of changing the choosing the samples,
Okay.
replacing calcium step by step by strontium.
And what strontium percentage in the alloy gave you the best results?
That's what we are going
Yeah.
to talk about.
So, what was the test schedule for the evaluation of the lead calcium tin strontium alloy for the positive grid of an SLI lead acid
Okay.
battery?
At the first step, because as you know, battery test takes a long time, maybe 2 or 3 months we need to find out that what is the real performance of a little change in the process. So in this case, I firstly start with electrochemical test and separate my test to two separated phases. First, electrochemical test, and second, battery test. In electrochemical test, properties including passive current density, PBO formation peak, and oxygen evolution reaction were assessed using potentiostatic and cyclic voltammetry technique. And in addition, the hardness measurement was performed for various samples. We had run a potentiostatic test to find out the real condition of the improvement that we can find, and for comparison, the measured passivity current density in potentiostatic test shows that strontium addition to the grid can significantly reduce the passive current density.
Passive current density.
Yes, and the corrosion rate considerably decreased with adding the strontium to the positive grid alloy. And the best results was for 0.02% strontium content alloy.
When you make it 0.02 strontium, do you reduce any other element in the alloy, maybe tin or calcium or aluminium?
Aluminium and tin, we try to keep the aluminium and tin constant in the alloy. As I already informed you, tin content is 1.2%, and aluminium is constant. Just the difference is the amount of calcium and strontium. Why aluminium is constant? Because when we add less calcium content, then we are adding less amount of aluminum in the alloy. But as I choose the strontium master alloy, same with calcium master alloy, the amount of calcium in both master alloys, aluminum calcium master alloy and aluminum strontium alloy, was same. So when I replacing the strontium with calcium, the amount of calcium was almost same in all samples.
I'm sorry, I didn't understand. Your aluminium remains the same because the aluminium strontium and the aluminium calcium, the aluminium is already part of the master alloy.
Yeah.
So you did not change that aluminium component
No,
in the alloy.
no.
But you did change the calcium
Yes.
component. So how much of calcium did you reduce or increase? What did you do? You reduced it?
The calcium amount is constant, 0.04, and I tried to change the strontium amount in different steps, from 0.01, second one 0.02, third one 0.04, and fourth one 0.06% aluminum. And because the most of normally in alloy making, when we are using aluminum, the main purpose of aluminum is to come at the top of the alloy pot and not allow the calcium to or strontium to be oxide. So mostly this is the main role of the aluminum. So the amount of aluminum is mainly constant because the most of aluminum will come on the top and will be oxided and will be separated from the alloy.
Okay, so now in the positive lead acid battery grid alloy,
Yeah.
Can you now, for the sake of the listeners, very clearly state how much was calcium, how much strontium, how much aluminium, and how much tin?
For aluminium, it's around, I think, I should check, but as I remember, it's between 0.01 to 0.02% in these alloys.
Okay.
For calcium, is a constant from 0.04%. Strontium is changing from 0.01 to 0.06. We have 4 samples: 0.01, 0.02, 0.04, and 0.06. And the tin amount is 1.2%.
1.2.
Yes.
Okay. Now you mentioned 4 strontium: 0.02, 0.04, 0.06,
Yes.
and also 0.01.
0.1.
Okay. Which gave the best results?
In potential static test, the best results was for 0.02% of strontium. It means
0.02.
the potential static test shows that less corrosion happen in this amount of strontium. But when we want to talk about the
Battery tests?
not
No.
later.
Okay.
Yes, we did the battery test. Later, I will explain. But in cyclic voltammetry test also, we had tested 2 things. First, we checked the PBO formation peak. In PBO formation peak, if I want to explain, the result shows that the ratio of PBO formation is lower with adding the strontium to the PB calcium tin grid alloy, and the best result is detected when the strontium amount is between 0.01 to 0.02%. That can cause better charge acceptance. In other hand, to compare the O2 evaluation reaction on the prepared alloy, the current density at 2400 mV per SC was considered, and the results showed that the adding strontium to PB calcium tin alloy will decrease oxygen evolution, and the best result is detected when the strontium amount is between 0.01 to 0.02%, which can cause lower water consumption. And in hardness test, until now, we can say the best result belongs to 0.01 to 0.02% of strontium amount. But in hardness test, when we measure the hardness and we made the acceptable range higher than 12 Brinell hardness to have a good pasting, to have a good strong structure of grid, 0.01% did not pass the hardness test. So back to your question, which amount has the best results? We found that decreasing strontium amount is better in this investigation, and but in the hardness test, 0.01 did not pass the hardness. So we can say that the higher corrosion resistance and good electrochemical behavior can be caused by strontium, but a sufficient amount must be added to get the acceptable hardness.
So 0.02 turns out to be good for all aspects?
Yes.
So now, finally, when we again talk of alloy, then calcium should be how much?
In this 0.04 in this investigation.
Calcium 0.04.
Yeah.
Strontium 0.02.
Yes.
Aluminium?
Around 0.01 to 0.02%.
Okay. And tin 1.5%.
1.2% in this investigation. Because tin is an expensive metal. For sure, increasing tin content can increase tin calcium ratio and can cause a huge improvement in corrosion resistance. So 1.5 is much better if the price is not important.
Yeah, but even with 1.2, did you get a similar corrosion resistance just because you've added strontium?
Yes.
Yes?
Yes.
So can we not then safely say that 1.2 tin is sufficient when it is a strontium alloy?
Yes, we can say that, because what is important is tin calcium ratio, not tin amount. So lonely, not the calcium amount lonely.
Yeah.
The tin to calcium ratio, because when we look to microstructure, the boundaries are important.
Yeah, they are
so
important.
yeah, so that's come from the calcium tin to calcium ratio, not tin lonely, not calcium lonely.
Okay. Now, again, when we talk of strontium being added, does it impact the cost very much?
Not too much, because the master alloy, we are replacing the master alloy. When you are using the lower calcium content, that means we are using less master calcium aluminum alloy, and we are replacing it with strontium aluminum master alloy, and the price is not too different, almost same, a little bit higher.
Okay.
I don't know about the India market, but in Iran is almost it is very close.
A little bit higher, is it? When you use
I think it is a little.
But then if you are able to reduce the calcium from 0.06 or 0.7 to 0.04, do you get some advantage?
Yes. We improve the corrosion resistance.
No, in terms of cost.
In terms of cost, but we are replacing with strontium.
Yeah. So it's almost the same cost?
Strontium is a little bit higher, not
bit
a big difference.
Not a big difference.
Yeah.
Okay. Okay. Now, did you test the effect of the lead, calcium, strontium, tin alloy on battery performance?
Yes. After finding the electrochemical advantages in electrochemical test results, we choose the sample 2 with 0.02% strontium amount, and sample 5 as a conventional calcium content without the strontium as a reference, and we prepared 266 ampere hour batteries with 6 positive and 6 negative plates by these two samples.
66 ampere hour.
66 ampere hour battery.
Oh, 66 ampere hour.
66 ampere hour.
Two numbers. One,
yes.
One with strontium, one without strontium.
Yes, two batteries.
Two batteries.
With the same grid casting, pasting, paste making, curing, assembly, and formation. Everything was same except the alloy. And the samples were tested according to PSA standard. PSA standard is a Peugeot Citroën standard, because in Iran, the biggest car manufacturer, Iran Khodro, is mainly producing Peugeot and Citroën cars. So this is a very common test in Iran. According to test results in C20 and CCA test, we found a little bit improvement, but the main improvement appear in charge acceptance and cycle life test. In charge acceptance test, we found that by using 0.02% strontium, we can achieve to 37% more charge acceptance.
37% more.
37% more charge acceptance.
So you could charge it faster or at a higher current?
Yeah. Yes. Higher current, maybe not, because higher current, many other things should be ready for higher current. But we can say faster with the same current. Yeah.
Okay.
And in a cycle life test, this standard is including 6 units, and each unit is containing 32 cycles of charging and discharging. So totally 196 cycle charging and discharging. And we did not stop the test and let the batteries to go on to find out when they really fail. And the failure point is dropping the voltage less than 10.5 during discharging. In this case, 0.02% strontium amount alloy passed 300 cycles, and the conventional alloy passed just only 208 cycles. That means we have achieved 44% more cycle in cycle life test. And after cycle life, I had run another test to find out what is the remain capacity after cycle life test. And in strontium amount 0.02 strontium amount sample, the C20 test after cycle life was 47.6, and in reference sample was 23.6. It means that with strontium amount in alloy, we can achieve to only 28% capacity lose, but in the reference samples we had lose 58% of initial capacity. And when we after cycle life
when you say 58% after 208 cycle or after 300 cycles?
For strontium amount after 300 cycle, still 28 just lose 28% of initial capacity. But in reference sample after 208 cycle lose 58% of initial capacity. Okay. And it means that the capacity lose will decrease. And when we break down the battery and check the plate condition, we had found that the loses active material from the grid structure was much higher in reference sampling compared with the 0.02% strontium amount alloy, and much stronger connection between grid and paste was seen compared with the reference alloy in strontium alloy adding sample. And I think we found a very good result in battery performance also.
Now, in both the cases, you found that the active material was lost.
Yes.
Right?
Yes.
So, did you not find any corrosion in the non-strontium grid?
In battery test or in...
No, after the cycles were over, when you cut it open. Now, the main purpose of adding strontium was for corrosion resistance.
Yeah.
But in both the failure cases, you found that the active material loss was detected.
Yes.
Did you not find any corrosion in the grid, in the non-strontium alloy grid?
Yes. This is one of the points. You know, for any scientific investigation, during testing, we will find new ideas for future. And in this case, we found that, as you said, that just the active material is separated, but no, we did not find many corrosion. So when we think about it, one of the items that make us to repeat this test at higher temperature is this idea, because corrosion mainly happens at higher temperature.
So maybe you will have to do this test at higher temperature to be sure that strontium gives you corrosion resistance.
Yes, that's why this was the first phase. For the second phase, we made two changes. These two changes is first increasing the test temperature from 25 to 60 centigrade degree to find out what is the real situation of the corrosion and other things in higher temperature, and also increasing the electrochemical test results cycles. In this investigation, we just did our test for 50 cycles, but in the second phase we will increase our the number of our cycles at CV test and potential and other tests to from 50 to 180 cycles. So two main change will appear in second phase, increasing the temperature to 60 centigrade and increasing the cycles to 180. Maybe the next year in next power on, I will present the results here.
Because the purpose of adding strontium was basically for corrosion resistance.
Yes.
And here I find that the final findings, what you got, were related to shedding. So, I mean, whether the batteries with strontium and the batteries without strontium, when both have when one has shed and the other has not shed, probably the one without strontium has been driven in a different in the vehicle in a different road condition, and probably this was driven differently, and that's why there's no shedding, and here there is shedding. This is a possibility which you will have to rule out.
Yes.
So then we can very confidently say that adding strontium to the alloy, there is no grid corrosion, because in this finding I find that in both cases there is no grid corrosion.
Yes, you're right. When we separate the test to electrochemical test and battery test, in electrochemical test, we found that we have improvement in corrosion resistance, oxygen evolution, and charge acceptance.
Yes.
But when we tested the battery, when we want to talk about the test results, battery test results, we found again charge acceptance improvement, but and we found the cycle life test as a,
Yes.
a good factor for.
I agree.
But yes, you're right. In corrosion, we did not find that the grid is corroded or not.
Yeah, no.
That's why we should increase the cycles and increase the temperature,
Temperature, yeah,
to
correct.
see the
Yeah.
if it is happening in the battery or not.
So, I mean, how do you put the electrochemical and battery tests in line together? Is this your finding that?
Yes, I try to make connection between these two types, because, as I told you, it is important even in the future that to choose, because the battery cycle life, battery test result mainly cycle life takes a lot of time. So it is important to find the closest amount and choose the best amount of strontium, and then they run the battery cycle life to save the time. In this case, I try to have a connection between electrochemical test results and battery test results. In electrochemical test results, we found 40% lower PBO formation peak. That indicate better charge acceptance. In other hand, we found 37% increasing in charge acceptance. They are very in line together. In electrochemical test results, more than 4 times lower passive current density in the potential static test can cause higher corrosion resistance. We found, and also 67% reduction in oxygen evolution current density that indicate lower water consumption. In other hand, we found 44% improvement in battery cycle life and 45% lower capacity loss after cycle life. That are related, I think, together. Maybe after phase 2 we can make a better connection conclusion between this type of test results together.
So, what is the next step?
The next step, as I already informed, is evaluating the PB calcium tin strontium alloy performance at higher temperature and more battery charging and discharging. So in this case,
more number of cycles.
Yes, we want to change the test temperature from 25 at first phase to 60 centigrade, and changing the number of cycles of CV test from 50 cycles in the first phase to 180 cycles in second phase. In this case, electrochemical properties including PBO formation, oxygen evolution reaction, passive current density, and corrosion resistance will be tested using cyclic voltammetry, potentiostatic, and EIS technique at 60 centigrade degree. And for future also, these results belongs to grid casting technology. In the future, I want to work on wide strip casting and narrow strip casting with this alloy, because this alloy is much harder in compare with the
non-strontium
hardness is much higher strontium content compared to
strontium
non-strontium. So what we can see that what is the behavior of this alloy during wide strip casting and narrow strip casting. and we already prepared the alloys, and we are going to send it to a battery manufacturer in Iran and ask them to make the wide strip casting and narrow strip casting for us. Then we can make a punch grid from them, and also test the punch grid performance with this alloy.
Yeah, good. Thank you very much, Mr. Ali. And in case somebody wants to get in touch with you and understand more about this, how do they get in touch with you?
This is my first time that I come to India, and it was my honor to be part of this 19th Pabaran conference. I think the conference sponsor has the connection, and also in India market they can contact to Listing Power as
Listing Power
as our cooperating company, and also I'm available in LinkedIn.
Yeah, you are available on LinkedIn.
Yes.
Okay. Thank you very much. It's been a pleasure talking to you and understanding so much about this new developments on which you're working. And I must thank you for agreeing to be on my podcast.
It was
and
great.
I look forward to listening more to you in the next Power On conference, or maybe even any other conference which you're doing earlier than that. And I'm sure you will come out with more results on this function.
Thank you very much.
Thank you.
Please do visit www.rameshnatrajan.in. Keep yourself updated about our new releases by hitting the subscribe button.